So we've been talking about the rigid rotator, the rigid rotor, if we want to go ahead and shorten that word. And we have basically assumed that our rigid rotor is two atoms. We're only looking at diatomics here. And the chemical bond between them, we are saying, is rigid. So it's not stretchy at all, which I know bonds tend to vibrate, but at regular temperatures, they might vibrate maybe 1% of the total bond length. But as soon as we start rotating these, the bond itself may start to stretch. And so if we have a molecule moving quite slowly, like this one over here, it's probably fair that that bond in between is not going to stretch too much. But if we rotate it a little bit faster, that is probably going to cause the atoms to actually go further apart and the bond will start to elongate. And so we can see now the molecule on the right, as it's rotating faster, that bond in between is kind of like a spring starting to stretch out, and that causes the molecule to actually increase its separation between the atoms. So let's go ahead and stop them spinning by zapping them, and let's go ahead and see what this does. So presumably as the molecules rotate, they start to lengthen the bond between the atoms. And how does this affect things? Well, we know our rotational constant is h bar squared over twice the moment of inertia. And h bar, of course, isn't affected by anything here, but the moment of inertia for a diatomic is the reduced or the effective mass times by the distance between the two atoms squared. And this is the term we have to watch out for here, because this term is going to change as it rotates. And so as it rotates, this term here will increase, so it'll increase upon rotational speed. So presumably the bigger J is, the faster it's rotating. And what's this going to do? Well, it's in the bottom, it's in the denominator. So if this is increasing with increasing J, then since it's in the bottom, this whole thing is going to be decreasing with increasing J. So B is going to go down as J increases. So what we'd expect to see, right, is that for faster and faster rotations, the rotational constant gets smaller and smaller. So there's a couple of ways to handle this actually, and the way we're going to go ahead and handle this is we're going to take our energy expression. So our energy is that rotational constant B times by J times by J plus 1. Sorry, got an extra parentheses there. And we're going to take that and we're going to imagine expanding this out in a power series. So remember, in a power series, right, we can take something like f of x, right, and we can say, well, okay, we can approximate it as a plus b times x plus c times by x squared plus d times by x cubed plus whatever it may be. And so in our expression here, right, we can take this as essentially our x, and we can go ahead and expand out, and here's how we're going to do it. So the line above, right, is going to be for a perfectly rigid rotor, and the line below is what we're going to use to accommodate the fact that as the molecule spins faster and faster, the value of B actually decreases, and that leads to a decreasing in the energy. So we're going to let the energy decrease by doing this. So we're going to go ahead and put a subtractive term on there. We're going to go ahead and we're going to use D for our constant here. This constant here is called the centrifugal. So centrifugal distortion constant. Okay, and by centrifugal, what we mean is centri means center. So, okay, fugal, just like fugitive, means it's running away from the center. So we are imagining the atoms, if you like, as they're rotating, running away from the center of mass. This is going to distort the energies. This is going to lower all the energies now because our value of B is going down. And we're going to handle it through this sort of power series expansion trick. And so we're going to take this J plus 1. So, and we're going to square this. So just like the power series expansion, right, we can add additional terms. So this is x here, and we're going to go ahead and square it. And if we wanted another term, we could cube it. So we're going to go ahead and write the J plus 1 as J squared and J plus 1 squared. So we're basically just squaring this whole term here. And what this essentially does is has the effect of dropping the energy levels as we go to faster and faster rotations. So on the left here in black, I'm going to have my rotational levels. Okay, we're going to ignore degeneracy for now. And so I suppose this is the 0, the 1, the 2, and the 3. Oh, maybe we'll put a fourth one. It should probably be off scale, but we'll cheat a little bit and look something like that. And in blue, so this is without basically the centrifugal distortion constant. And if we introduce, and so we include the distortion constant, and we'll just go ahead and jot that expression down on the side. So we said EJ is BJ plus 1. And then our correction terms are minus D, and then we're squaring the J's that appear. There we go. So we can see that as J gets bigger and bigger, right, we're squaring these, so we are subtracting off a larger and larger component from the energy. When J is 0, there's absolutely no change at all, because we subtract 0 times anything, right, it's not going to have any effect at all. But as we introduce J to 1, then we're going to be subtracting off a very small amount. So the energy is going to go down ever so slightly. And as J gets bigger and bigger, this becomes a bigger and bigger effect. So when J is 2, that squares to 4. And so it's going to have a higher effect. When J is 3, that squares to 9. So as the J gets bigger and bigger, right, we're going to be subtracting off larger and larger amounts. And so we can see that all these levels, right, so initially, right, there's no change at all. And then we see a very slight decrease. And as we go to J equals 2, right, it's spinning faster and faster and faster. So the energy is going down by a larger and larger amount as that bond distorts. And as we go up 4, 5, 6, and up the ladder, we can see some serious distortions taking place.